Welcome to your video on variation. You will notice for your homework this evening to check the sideboard in the classroom, figure out what you need to do over the next few days. In addition to in your notes, there are the homework assignments listed at the stopping points in each one of the videos. We are going to start today at the very top of your note sheet. And this is actually something that I want you, after I explain it, to pause the video and read and try to write down any examples that you think. So we have two types of variation that we're going to study, our direct and inverse variation. Before you even know what these actually are, you're going to think of examples that fit into the two categories below. So first of all, number one, as one variable increases, so as something grows or gets bigger, you have a different variable that also increases. I want you to think of any example that you can that fits into that first category. In the second example, now you're thinking as one variable increases or goes up, then the second variable will actually go down. So stop the video, please write down examples that you think, and we'll talk about these in class when I return. Now, as we're actually looking at these two parts, the very first type of variation that we're going to study is something called direct variation. The actual definition for direct variation is as one quantity increases, another quantity increases proportionally. So that means as one thing gets bigger, another thing will get bigger at the same time. So an example of this is if any of you have a job, the more hours that you work at that job means more money you are going to get. Okay, both of the variables, x and y variable, would be going up as this scenario played out. An equation that is associated with this is something along the lines of a y equals, and then you'll notice this k times x. This is very similar to slope-intercept form, and you'll notice that this k value is the constant that is actually going to be in every single one of these problems. Essentially, what the constant is for direct variation is slope. It's the number that in some way, shape, or form is going to be always in your problem. If we're thinking of the example of the working more hours, your constant would be how much you make every hour, whatever your wage actually is. Now, there's going to be some times where we actually have to go through and solve for that k value or solve for the constant because we don't know what the constant actually is. So in order for us to do that, you'll notice that all we have to do is essentially divide both sides by x, and that's how we wind up with our k equation. That would be equal to our y over our x. So again, in a little bit, we're going to be doing some examples where we have to solve for the constant, and you can use either one of those two equations. So how do we say what is actually being described here? One way in your homework that you might see it described as y varies directly with x. So that means your y is the part before the varies, which means the part before the equal sign. And well, what is directly with x? It's your constant, which for this is why you would have your y equals your constant times your x value, because the constant varies directly with your x. If you're looking at the second phrase, again, same idea, same exact equation, we have y is directly proportional to x. So again, the exact same equation would be what we wind up with because it's direct variation, which means we would have multiplication. As we're looking at, I would say, an actual example of what direct variation is, it says in California, the cost of electricity is directly proportional to the number of kilowatts used. A resident that consumes 4,000 kilowatts an hour is billed $480. Write a mathematical model that describes the cost in terms of the kilowatts per hour. So in this case, what we're trying to do is write down initially the information that we know. So this is a direct variation equation because we see the magic words. What is before the actual directly proportional? It's the cost. So we have our C, or our cost in this case, that is going to be equal to, well, what is it directly proportional to? It's the number of kilowatts per hour that are used. So we have our K times, and well, to say kilowatts per hour, we can't actually use a K because that's what we have for our constant. So I'm just going to say our W, which again, in this case, is our kilowatts per hour. So if we make this equation, it's actually C equal to our K times W. Now the goal is, when it says to write a mathematical model, we want to solve for what our K value actually is. So in this case, we know what the cost actually is. You paid $480. We don't know what the K value is, and we do know how much wattage they use, which is our 4,000. And now what we can do is to solve for this K value. So as we're going through, we divide both sides by a 4,000. So we end up in our calculators getting a 0.12 that is equal to our K value. What this tells us is this is the amount of money that you get charged for every kilowatt per hour that you use. This was the same example where we talked about on the last page, where you had a base wage, an hourly wage. That's exactly what you're finding here. So our final answer would be your C is equal to your 0.12 W. And now we can be given any situation and accurately be able to describe that. Now, let's go on to the second part, inverse variation. So as one quantity increases, another quantity is now going to decrease. So as one goes up, the next goes down. An example of this is the cost of a song. If you're buying a song from iTunes or you're listening to a podcast, whatever the case, if that song continues to go up in price, the number that is actually going to be sold eventually will start going down. Okay, one thing increases while the other decreases. So the equation for this is now a fraction. All you knew was coming at some point, where now we have our y that's equal to our k divided by our x. Our k is still our constant as we are going through here. So the k is still our constant of proportionality. And again, a few different ways to write this. If we're trying to solve for our k value, technically, based on some of the algebra that we've been doing the last week in here, we know that we would have to multiply both sides by x. Well, the x's cancel from the right-hand side, which is why we just get our k, and we multiply the x times the y. We get our equation to find our k value. Now, a couple ways to say an inverse function. We have y varies inversely with x. When you see that word inversely, that tells you right away that your x value is being divided by your constant. If you look at the second phrase that we have, same idea, y is inversely proportional to x. So that means the inversely proportional means your x, again, has to be underneath your k value. So now let's get an example of an inverse variation problem. So if we look at this, we would say in New York City, the number of potential buyers in the housing market is inversely proportional to, that's already a huge part there, is inversely proportional to the price of the house. If there are 12,500 potential buyers for a $2 million condo, how many potential buyers are there for a $5 million condo? So the first thing we're trying to do is set up this equation. So it says the number of potential buyers is the information before we reach the inversely proportional. So we have our B, we'll say, for our buyers. So our B has to be equal to, well, we know our K value has to be on top. And in this case, because it's an inverse, we know we have a fraction here. And it says the actual price of the house. So you can use whatever letter you would like in this case. I'm going to use P for my price. So the equation that we're going to use in this case is B equal to K over P. Let's again fill in some information here to try to solve for our constant. We need to solve for that K value. We know how many buyers there are. There's 12,500 buyers that could afford in this market a $2 million house. You have some options on how you want to write 2 million. Okay, you can write out all the zeros after that if you so choose. I'm going to just write the 2, and you'll see what that means for our final answer as we go through. Okay, so now I'm solving for my k. I multiply both sides by 2. So that means that I have 25,000 possible buyers in this market, okay, that could afford any given price point for a condo. So that means if I have a $10,000 place, a $10 million place, this is our constant as we plug other values in. So now the difference with this one is we have a K, and they're asking us a question to solve for how many could buy a $5 million condo. So your goal is to think, okay, if at 2 million, there were 12,500 people, should your answer be more or less? And I can hear the gears turning as you're thinking about this right now because the price went up, which means the buyers has to go down. That's the definition of an inverse function. So what I have to do now is plug in this case, my B is the answer I'm looking for. I plug in my constant that I have, my 25,000, all divided by, well, my amount of dollars going for the condo, the $5 million. When I divide these two out, I get my answer to be 5,000 total buyers that would be able to fit this price point based on what we're looking through there. So as we're going through, not only did we write the equation, we found our constant, and then we plug that constant back in for our inverse variation. Now, the next is kind of lumped together, and this is one that's not as commonly used. It actually happens a lot more in math with some equations that we have. So it's something that's called joint or combined variation. So joint variation is when one quantity is proportional to the product of 2 or more, which means you're taking and multiplying the K with 2 or more, and I'm going to call them terms in this case. All right, and you see the example that I have is your volume of a cone. You have a 1/3, which is your constant. The 1/3 is always there. In this case, you have the constant right there. And you're multiplying with it a pi, an r squared, and an h, all being resulting in your product. The second part here, and combined variation, actually happens a lot in science. All right, with combined variation, it's when direct and inverse variations happen at the exact same time. So with a lot of laws that we have throughout chemistry, your equations have multiplication and division in them. So what that means, again, is when multiplication and division actually happen. So you'll notice that in this equation, we could also rewrite this to be something just a little bit different, where we have our P is equal to our K divided, or sorry, excuse me, K times T divided by your V. Whereas you're looking through, those two pieces of information are both in your numerator being multiplied, and then the V is where the division comes into play in that particular equation. Okay? Now, the last piece of information is, well, I have some pieces that we could look at as you're going through. So if you're reading what is actually being said here, you'll notice that I have another situation that deals with gas. So it says the gas in a soda bottle has a volume of 9 milliliters. It has a pressure of 2 atm and a temperature of your 298 degrees, and that case stands for Kelvin in this case, which is no different than saying you have 77 degrees Fahrenheit. If the soda bottle or the pop bottle is stored in a fridge, the temperature then drops all of a sudden. That temperature drops to about 279 Kelvin or 42 degrees Fahrenheit. What is the pressure of the gas when it is actually chilled? So we're using the same equation that was on the last page. So if we're filling that in, we have a pressure that we know that is actually our 2 atm. We have our constant that is here, that is being multiplied by now whatever we have for the temperature on top, which is our 298, all divided by, and now how much of the actual substance we have. So in this case, we have 9 milliliters of that particular soda. So if I'm going through and I'm trying to solve this, again, I can multiply both sides by my 9. I end up with my 18. That's equal to my K times my 298. I multiply both sides now by my 298. And my constant is going to be equal to a 9 over 149, or you do get a decimal that you could choose if you write it out into a decent amount of spots. So we found what our K value is. The question is asking us, what's the pressure of the gas when chilled? So then what we have to do is use that K value and actually plug this back in. So if we actually go through and do that, I'm trying to find how much pressure I'm actually dealing with. I know my constant is a 9 over a 149, and I multiply that, well, by the next piece of information. When it's chilled, what is the temperature? The temperature is now 279. The temperature changed. How much of the substance do we still have? The exact same. That doesn't change whatsoever. And as we go through, we can use our calculator to solve this. You get an approximate here because it is a decimal, but of about 1.87 atmospheres or ATMs we're going through. So we went through an example of each one of the types of variation. So now as you're going through, here is where you're going to practice, and this is really what your homework is going to look like. As if a variable z is directly proportional to x and inversely proportional to y, the relationship of those variables can be expressed in the form, and I wrote that in for you, z equals your k times x all divided by your y, where k is the constant of proportionality. So what we're going to do is we're going to find what the equations are for each one of these examples. So it says the volume of a cylindrical container is directly proportional, that's the key part there, to its height and the square of its radius. So what's the part before the directly proportional? It's our volume, it's our V. So we know all of these things are going to be multiplied together. So what are we multiplying with that constant? All of the stuff that's after the directly proportional. We're multiplying with its height, so I'm going to put an h in this spot, and the square of its radius, so I have an r squared. We've actually now written the equation for a direct proportional. For B, it says the force F required to lift some object with a lever is again directly proportional, so that's interesting, to the mass M of the object. Oh boy, and now it says inversely proportional to the length of the lever R. So if you notice here, we have a direct and an inverse in the same question. So it says the force F. So we know that F is going to be the part before the equal sign because it's the part that's actually before any of the proportionality starts. And it says directly proportional to the mass. Well, what's directly proportional to the mass? The constant. So we have our K times N. The inversely proportional starts out now because, well, we have a fraction, and if we're inversely proportional to the length, well, that means in the bottom, the L has to be fully in your denominator. And as you're going through, if you're reading the very last example, it says now the attraction F between two objects in space varies directly with the product of their masses m1 and m2, but it's inversely with the square of the distances e between them. I want you to pause this video, try this on your own. I'll write the answer up here as you pause it. All right, hopefully you paused that piece. The answer is all of the directly proportionals as your masses in your numerator and your d squared, or the distance, in your denominator. So now we have what our second and final answer actually is for this part. If you are interested, you can stop this video right now and start the homework that we will continue to work on, page 309, numbers 1 through 35 odds. Once you're continuing now to the next part here, this is going to be the key information that's going to help you with the second part of your proportionality information. So now we're going to look at this based off of a graph. So if we're looking at an equation that involves direct proportional or direct variation, we have our constant that is multiplied by our x. We said originally that this was your slope. So if that's your slope, we can really use any example that we want here. We could say that y, and if it's a slope, we can give any number. I'm just going to give the number 2 in this case. All right? And if we do that, we could easily graph where we know we have a 0, 0 point. We go a rise of 2 and a run of 1, and we could keep making this all the way through, go in either direction for this nice line. So one thing to note here is that your graph for any direct variation should always be linear. That's going to be one important part. And because we don't have any y-intercept, if we're looking at our y equals mx plus b, we have a linear equation with a y-intercept of 0. That is one important thing to note where it says, what do you notice about direct variation? Okay. The second piece of information now comes from the table of values. So if we're filling this table of values in, we know we have the point 0, 0. That's an important point because it's our y-intercept, and it has to be in your direct variation question. Okay. If we go and put a 1 in there, we get a y value of 2. If we put a 2 in, we get a y value of 4. We could keep going because we know if we put a 3 in, we get an x or a y value of 6. So even though it looks kind of funky, what's happening to your x's right now? Your x's are increasing. So as your x's increase, what happens to your y's? Your y's will also increase. So the second thing to note about a graphical approach or based on your table of values is that as your x goes up, then your y goes up as well, which if we remember some of our properties about direct variation, hopefully that should make a little bit of sense. If we look at now our inverse variation, we know that our equation is our y equals our k over our x. And if we look at the graphical approach, again, that constant can be absolutely any number that you want. It doesn't matter what number that is. I'm going to pick the number 10 as we look through here. And some of you see this equation, you see a fraction, you know that there's going to be a couple important things here. The first important point is that we have a reciprocal function. The reason that we have a reciprocal function is, here's the good joy of this, we have an asymptote that is created here. So if we're looking at that graph in some way, shape, or form, we hopefully remember from our family of functions that we have, voila, your reciprocal function that in this case has an asymptote at 0, both on the x and on the y. So if we plug values into our table of values now, and we're going to look at the same approach that we had before, technically, I hope you realize that we can't plug 0 in. 0 is going to get us an undefined answer. So what we're going to get is any numbers. If we plug a 1 in there, we get a 10. If we plug a 2 in there, we get a 5. I can pick any numbers I want. If I plug a 10 in there, I'm going to get the number 1. So now, as our x's are increasing, which they are, our y values are decreasing. So our second rule that we actually have as we're looking through this, and again, we remember what we know about our x's and our y's, we know that as your x or one variable increases, your y or your other variable decreases. So that's the huge difference when you're looking at a table of values compared to the graph as you're looking through. If we continue to do this, and if we are given a word problem that maybe doesn't have a specific description as whether it's direct or inverse, you can still find that out. So it's for each described relation, describe whether it is an example of direct variation, inverse variation, or neither. So as you're looking through here, explain your reasoning. Because if a runner can average 5 miles per hour for a long run, the distance covered is a function of the total running time. So, what we need to figure out is we're talking about the distance covered and the running time. So, if we're looking at our time, as our time increases, what happens to our distance? Our distance goes up as well. So that means both of our variables are going up, which means we have a direct variation example with our runner. So now the second part here, it's still a running example, but be careful of the wording. It says for B, if a marathon runner covers 26 miles, the average running speed for that race is a function of the time it takes the runner to complete it. So it says the running speed and the time it takes to complete it. So I know this isn't maybe 100% true because you have some really fit people, but typically the longer you run, what happens to your speed? Unless you're Mr. V, your speed would, obviously go up. But in any normal situation, your speed's going to go down the more you run, the longer you run. So in this case, we have a little bit different example where we are looking at an inverse function in terms of your variation. Now, the C that you look at here says in any square, the side length S and the diagonal length B are related by B divided by S equals the square root of 2. So literally what it gives you here is a whole lot of information that doesn't make a whole lot of sense. It's not asking you to compare necessarily anything you're going through. It just gives you the picture. So your goal in this equation is to try to get one itself. So if you do that, just like any other problem that we've done, we need to multiply this by S to both sides. We have a D that's equal to our square root of 2 times S. So now you're looking at that equation, you're saying, is this direct or is this inverse? There is no more division anymore because one of the letters is fully by itself. So you have an example of direct variation. The last piece of information I have for you, since I always get called Scrooge or a Grinch, I figured I'd give you an example that deals with Santa and Mrs. Claus. So when Mr. and Mrs. Claus were asked to explain how they recognize graphs of direct variation functions, they said the graph has to go through the origin 0, 0. Give explanations or counterexamples to justify your answer to these questions. So A is asking you, does every direct variation graph contain 0, 0? So for something to be direct variation, one of its definitions was that it's linear and it had a y-intercept of 0. So this answer, Mr. and Mrs. Claus, is definitely a yes. It's one of the rules of direct variation. So we have to have a line that goes through 0, 0. So that answer is yes. For B, it's asking, is every function with a graph that has 0, 0 on it an example of direct variation? So your thought process is you're trying to figure out if there's any graph that has 0, 0 that isn't a line. And there's a couple options that, especially you've been working with them last week. Okay, there are definitely other graphs that don't make up a line that still has a point 0, 0 on it. So the answer to this is no. Our counter example could be y equals x squared or y equals x to the third. Both of these have the point 0, 0 in it, and they don't make up a line. And they don't form anything in your y equals mx plus b. Okay? So as you're going through this, a little bit of thought process for your, I would say, last piece of information here. So please go through, finish the rest of your assignment. There are worksheets, there are book pages that you can work on at this time.